Dear chairs and authors, today we are here to give a presentation about our paper named DCNMF, Dynamic Community Discovery with Improved Convex-NMF in Temporal Networks. Well, for its crucial importance in the study of temporal networks, techniques for detecting community structures and tracking evolutionary behaviors have been developed. Among these techniques, evolutionary clustering is an efficient method which unveils substructures in complex networks and models the evolution of a system. Most research works in this domain mainly employ semi-NMF to discover evolving communities. However, in some cases, it cannot jointly maintain the quality of community detection and track the temporal evolution infallibly. Let's see what problems are there in dynamic community discovery, i.e. DCD. A major problem of DCD is to identify stable network decompositions, which comes from the very nature of communities. It lies in the fact that generally it is difficult to know if the differences observed on complex networks between consecutive time slices are due to the algorithm's instability or the community's evolution. In this paper, we propose a novel model which detects and tracks dynamic communities with convex non-negative metric factorization, i.e. Convex-NMF. It is based on an evolutionary clustering framework. In most of existing DCD works using non-negative matrix factorization, it is more common to apply semi-NMF to address concrete problems. The main contributions of our paper are as follows. Firstly, we propose a unified model DCNMF which detects communities and analyzes their evolution. Using probabilistic community membership and temporal smoothness constraints, the proposed model unveils latent community structure and discovers network changes. Secondly, by employing Convex-NMF to obtain community membership matrices, the proposed model achieves community discovery results that are of a better quality than semi-NMF solutions. Thirdly, the proposed model is easily extended to the network whose number of nodes and communities may change over time, which is a fairly common phenomenon in temporal networks. Lastly, an optimal algorithm is proposed to solve the obtained objective function. We prove that the algorithm is guaranteed to converge and verify the correctness of the algorithm. Analysis of its computational efficiency is also provided. As for related work, the available methods can be classified into two categories: heuristic algorithms and low-rank approximation approaches. Actually, there exist some issues in terms of these methods, like the major drawback of the multi-objective approaches is that the random generation of initial population will greatly increase the search space and hence cause high spatial and temporary complexity. However, the proposed DCNMF is capable of coping with the instability problem while not diverges much from the common community discovery. It takes advantages of partition search for at time step t-1 to speed up the community discovery at time step t. Then, here is the unified DCNMF model formulation as shown on the slide. We restrict central node column vectors to convex combinations of the columns of xt to achieve good interpretability of obtained matrices. For one thing, the basic matrix columns would capture the notion of central nodes whose movements often influence the drifts of nodes who have close relationship with them. For another, restricted constraints lead to the desired NMF solution that community membership matrix GT is more sparse and orthogonal, which gives sharper indicators of the community. To achieve evolutionary clustering for DCD, we solve this by maximizing the community detection quality of current time step and minimizing the historical cost. Then the obtained cost function is as formula 2. In addition, the proposed model can be easily extended to the network, including insertion and removal of nodes and communities. Assume that at time t, N1 nodes are removed from and N2 nodes are inserted into the dynamic network. The basic idea behind this heuristic is that we assume that these N2 nodes already exist as isolated nodes at time t-1. Moreover, we just preserve the membership of unchangeable nodes between successive time steps. Assume that at time t, C1 communities disappear and C2 communities emerge in a dynamic network. It is equivalent to assuming that the disappearing communities at time t split or combine with other communities. After that, the proposed algorithm will be introduced. The algorithm iteratively updates WT with GT fixed and then GT with WT fixed using following updating rules. And in such a way, the objective function defined in equation 2 is monotonically decreased and therefore converges to an optimal solution. The updating rules are as formula 3 and 4, and also the normalization of weight matrices W is required. The overall procedure of DCNMF can be described as algorithm 1. The inputs are xt, xt-1, k, and alpha. The xt is the agency matrix of the network at time step t. The xt-1 is the adjacency matrix of the network at time step t-1. And the k is the number of communities. The alpha is the temporal smoothness trade-off parameter. The outputs are WT and GT. The WT is the weight matrix of nodes at time step t, and the GT is the community membership matrix at time step t. Then here are the steps of the algorithm. Firstly, initialize WT/GT with random values. Then repeat the following procedure until convergences. The procedure includes the following steps. Update WT using equation 3 with GT fixed. Update GT using equation 4 with WT fixed. And then normalize the matrix matrix W. To verify the accuracy and feasibility of the proposed algorithm, we perform experiments on several datasets and we report the main results. In experiments, we evaluate the performance of the proposed algorithm DCNMF and compare the results on different types of synthetic and KIT email real-life datasets with 4 popular methods: Fist-Night, Demoga, Affect K-means, and Affect Spectral. As FistNet and FACT are two classic algorithms among evolutionary clustering methods, we choose them as baselines. We specifically select 3 synthetic and real-world temporal networks to assess the performance of the proposed method, where the synthetic networks are to prove the accuracy of the algorithm, and the real-world one is to validate the feasibility of the algorithm in practice. In order to measure the DCT performance, we select 3 evaluation indexes which are widely employed, i.e. normal mutual information, NMI, error rate, CA, and F-score, whose formulations are shown on the slides. In terms of synthetic dataset 1, dynamic GN dataset. It can be concluded that the proposed algorithm DCNMF is more accurate and robust on various networks of dynamic GN dataset aiming at DCT problem. In terms of synthetic dataset 2, dynamic LFR dataset, to obtain a synthetic network that is more consistent with the real-world network, we employ the extended LFR model to generate dynamic networks, which is based on the embedding of events into synthetic graphs. We test the proposed algorithm on the synthetic datasets, which mainly include the node switch event, i.e. node switch community membership between consecutive time slices. As for KIT email data, we can see from the tables that although DCNMF does not always perform the best on datasets, it is quite competitive with the best ones, i.e. FistNet, on NMI and CA. Overall, the proposed method DCNMF shows superior performance on NMI and CA compared with other methods. For our future work, we consider that one of the potential issues is that the long-term coherence of dynamic communities. For the reason that at each iteration, the detected community depending on previous ones. Temporal trade-off approaches are subject to the risk of an avalanche effect. Communities can experience rapid changes. Under such circumstances, it is more suitable to directly employ static community discovery algorithm for solutions at a given time. And it will be our future work to capture such substantial drifts in temporal networks. Furthermore, we also plan to extend our model to networks whose number of nodes and communities may change over time.